Okay, this is a short video by Dr. Shan about design of experiment. Okay, this is designed to accompany the lecture note with video record embedded. Okay, so we will see how to do a DOE in Minitab. Okay, so first let's go to slide 11. Okay, where we have an example. Okay, so here we have two factors. One is number of computer programs opened. Another is the memory size from 32 megabyte to 128. So we have 3 levels of B, factor B, and 4 levels of factor A. Okay. Now let's first take a look at how to design an experiment with Minitab. So you open Minitab. You go to Stats, go to DOE, go to Factorial, and create Factorial Design. Okay, so here you can see there's a number of different options for types of design. Okay, so the first one, first 3 actually are for 2 levels. Okay, so you can have, so for example, for the first one, you can have 2 to 15 number of factors, and each factor will have 2 levels. Now, and then Plankett-Berman design is a fractional factorial design. Now, if you have more than 2 levels, you can go to general full factorial design. Okay, and you can also choose number of factors. So in our example, we only have 2. Then you hit design. Okay, so you can see for the first row is factor A, so the number of level we input 4, and then for B we have 3. Okay, and then here because the number of replicates is just 1 in the first example, so we will keep it like that, and then we hit OK, and then we hit OK. Now you can see there's a number of outputs. First, you can see from the output of the Minitab, it's a mini level factorial design, and then it has design summary. So you can verify that you're inputting the right number. So for example, factors is 2, so base run is 12 because we have 4 levels of factor A and 3 levels of factor B. So 4 times 3 is 12. So base block is 1 because we only have 12 experiment or test case or run, and we do not differentiate, right? We do not separate them into blocks. And the replicates, we only have 1. Okay. In another later example, we will see when we have 2 replicates. So the total run will be 12. Again, 4 times 3. So the total block is 1. Number of levels is 4 and 3. Okay. So these are the outputs from the Minitab. Now let's take a look at in the worksheet part. It also gave you 12 rows corresponding to the 12 runs. Okay. So if you make it larger, you can see the first column corresponding to standard order. Okay, so you can see this is from 1 to 16, but in randomized order. Okay, sorry, 1 to 12, corresponding to the 12 experiment we're going to run, or 12 conditions. Okay, so the second column corresponding to run order, so it tells the experimenter which condition to run first. So from 1 to 12. And column 3 and the column 4 are not something that we will use, so we can ignore that. Now column 5 corresponding to factor A, and column 6 corresponding to factor B. So this tells us in the first run, so in the 12th run, what are the levels of each factor that we should set? So for example, for the first one, so it's run 1, but actually in the actual design, the standard order is 12. Okay, so you can see this corresponding to when factor A is at level 4 and the factor B is at level 3. Okay, and then the second one corresponding to standard order 8. Okay, this is when factor A is at level 3 and the B is at level 2. So you can easily verify that we vary factor A from 1 to 4 3 times for each level of B, and then similarly for level B, for factor B, we also have 3 levels, and each level will be repeated 4 times, corresponding to 4 levels of A. Okay, so this will be our experimental design. What we need to do is we need to input our response. Okay, so the first response, again, go back to the slides, will be 0.25. Okay, and then you can continue to type in. Well, sorry, actually, if you type in 0.25, that might not be correct, because 0.25 corresponding to A at the level 1 and B at the level 1, which is 32 megabyte. So actually, you should be looking for A at the level 4 and B at level 3. So that's 0.70 in the slide. Okay, corresponding to the bottom right case. Okay, so you need to be careful about this. Okay, so the second one, let's do another example. The second one is when A is at level 3 and B is at level 2. So A at level 3 and B at level 2, it's 0.66. Okay, so you will repeat in this fashion until you input all the 12 cases. Now, you can also cheat. I upload a file corresponding to with all the response already typed in. Now let's take a look. Okay, so I just opened the data file that's provided to you. It's called computer response time single replicate. So I put the one that I just created, the design that I just created, along with the file that I uploaded. Okay, so if you compare, you can see the sequence for standard order are different. Okay, so the run order always go from 1 to 12, and as a result, you can see the column 5 and 6, the actual design is a little bit different. Okay, so for example, for the first row, we have standard order 12 in the data file, which is also the first row in the one that I just created. So the response is still 0.7. Okay. However, for the second one, that's the standard order in the data file is 6, while that I just created, it's 8. Okay. So the response time will not be the same, right? However, if you looking for the standard order corresponding to 6, which is A at level 2 and B at level 3, and then you go to the slides, you will find the response time, which is 2. Okay, from the PPT, you can see when A is level 2 and B is at level 3, the response time is 0.36. Okay, 0.36 if you have to type it yourself. However, if you use the data file that I provided, it will be in row 2 because the standard order is 6. Okay, so we will be looking for the standard order because the sequence of standard order will be different every time when you create a new design. Okay, so so you need to pay attention to what it corresponds to. Okay, in terms of levels of the factors. Okay, now let's say that you have this. Now let's say that you already input typing order response time and you want to analyze this. You will go to DOE, fraction, factorial, analyze factorial design. Okay, so you will double click response time. Okay, and you have a number of different options. Okay, so for example, if you go to option, here you can see the confidence level for all intervals. So basically, one of the output will be some hypothesis test. This is where you set the alpha level. Okay, and the graphs give you different options. You can by default it will you can choose to display histogram, normal plot, and a residual plot. Okay, so the histogram and those plots are mainly to verify whether those data are normally distributed, because some of the basic assumption of the this experiment is all the values are normally distributed. So the residual plot should also look random. Okay. You can check out all the options by click on different buttons. Now if we click OK, so you will see this is the result of the analysis. Now you can verify from the factor information that we do have two factors. One factor A has 4 levels and factor B has 3 levels. Now you look at the analysis of variance. Basically, you have linear term to main effect, right? And then two-way interactions. Okay, linear basically meaning that is just referring to main effect. Okay, so there's no interactions. Interaction will be a higher order. That's why it's called linear. But interaction could be two-way interactions. So for example, in this case, but it could be three-way interactions or even of higher order. Now, as you can see, we cannot really do any ANOVA here, right? Because it cannot calculate F value. Now, the reason for that is we only have one replicate. Therefore, you can see in the row corresponding to arrow, it cannot calculate because we only have one per condition. Okay, so we need at least a 2 in order to calculate the error term, which are supposed to represent the random error, right? And then all the other test statistics is based on a ratio between the MS and for that factor or for interaction factor and versus the mean square for the error, right? Because we cannot calculate the mean square for errors, we cannot calculate the test statistics. Okay, so that's for one factors. Now, with only one replica, you cannot test for significance. However, you can still examine the plots, the main effect plot and the interactions. So the way to do it is go to DOE, factorial, and then factorial plots. Okay, so you can select both factors. If you go to graph, you can check the main effect or the interaction. Okay, and the interaction, you have two options. One is only display one plot. One is playing the all plots. Okay, so for example, if you have two factors, so one is factor A, one is factor B, and then display lower left matrix will give you the plot corresponding to A times B, while display fourth matrix will show you both A times B and B times A. Okay, So let's say that we select display full factorial, full matrix, and OK. So you can see from the interaction, you have two plot. So the one on the bottom corresponding to the case A times B. So in the horizontal axis, we have 4 levels of factor A, and then the 3 line corresponding to 3 levels of factor B. On the other hand, the one on the top shows you horizontal axis is 3 levels of B, and 4 lines corresponding to 4 levels of factor A. Okay, so if we look at this, so we can see that the largest response time corresponds to when the factor B is at the lowest level, so smallest memory, and factor A is at highest level, that is have a lot of program open, have 4 programs open. Okay, that's the largest response time. On the other hand, the smallest response time, the quickest response time, corresponding to when the memory size is the largest at level 3 and number of program open is smallest at level 1. Okay, so you should be able to draw the same conclusion by looking at the other graph. You can see this blue curve dot here corresponding to when factor A at level 4 and the factor B at level 1. Okay, so meaning that 1 program open and corresponding to the smallest size memory size and the 4 programs open. Okay. On the other hand, if we look at the green dot down here, corresponding to level 1 of factor A, that is only have 1 program open, and the blue curve corresponding to level 3 of B, factor B, so meaning that the largest memory. Okay, that gives you the quickest response time. So the same conclusion will be drawn from both. Now then you will look at the main effect. So the main effect, first we look at A, factor A, which is number of computer programs open. So as you can see, as the number of computer programs open increase, the response time will also increase. So there's a positive relationship here. But a linear relationship is not necessarily true, right? So in this particular case, it's happened to be true, but in many cases, it's not true. Okay. If there's no effect, no main effect, there will be a flat line. But any fluctuation around the flat line will also be possibly indicating a main effect. Okay. So on the other hand, for factor B, you can see as the memory size increases, the response time will decrease. So there seems to be a negative effect, negative relationship. Okay. So both of them will suggest significant effect. However, we don't have any hypothesis test for us to test this claim, right? With only 1 replicator. Thank you. Now, if you go to slide 14, you can see all the data for the computer experiment with 2 replicates. That means for each of the combination of 2 factors, so for example, A at the level 1 and B at the level 1, which is 32 megabytes, you record 2 response time. One is 0.25, one is 0.28. Okay, so now let's see how can we do this design experiment with Minitab. Again, we go to DOE, factorial design. Okay, so we still have 2 factors. You go to design and then change this to number of replicate to 2. Okay, then you hit OK. Okay, so it should give you a 2 replicate example, right? So we should have 24 runs. Okay, so in the one without with only 1 replicate, we have 12 runs. Now we have 2 replicates, so it's 24 runs. Each of the condition we will run it twice. Okay, so you can easily verify that the standard order goes from 1 to 24 in a random sequence, and factor A should be run at the 4 levels. Each of those levels will be run at 3 times, and each of the 3 times will be run 2 times for to replicate. Okay, so again, you can input the data as provided in slide 14, but just pay attention to what number you input. So for example, so the first row should be A at the level 1, B at the level 3, so it's 0.15. Okay, so you can and also the second one is when A is at level 1, B is at level 1, it's 0.25. Okay, so you can complete that in this fashion. Now you can also open the data file that I provided. That save you some time for typing. Just remember that every time when you design a new one, the standard order, the sequence for standard order might be different. Okay, just be careful about that, and also be careful when you input the data. Okay, thank you. Okay, so I opened the data file provided. So we have recorded a 24 response. Okay, now let's analyze it. Go to Stat, DOE, Factorial, Analyze Factorial Design. Okay, our response will be response. You can check the covariate option. Right, so we do not change anything. Now if you hit OK, you can see now we have some analysis of variance. Okay, you can still verify the factorial information. There's some options. You can send this to Word. Okay, and I'll send this to PowerPoint. Just right. Okay, so you can see in the analysis of variance, factor A is significant. Factor B is also significant. And the interaction between factor A and factor B are also significant. Okay? And also, you can look at the graph. Okay, so go to DOE, go to Factorial, go to Factorial Plots. Okay, so here, you can select both of them to be the to generate the main effect. Okay, so and you can click on graph, so you can check the main effect plot and interaction plot. So if this one is checked, they will only show one interaction plot. Now if I click on this one and then click OK, and then click OK, you can see both the main effect for factor A, which is number of program opened, and also the main effect of factor B, which is memory size. Okay, so as you can see, actually usually you will first look at the interaction term to see if there's significant interaction effect or not before you analyze the main effect. Okay, so here in the interaction plot we can see we have 2. Okay, so this is very similar to the plots with 1 replicate, right? So basically 2 replicate, every point here is just representing the average of those 2 values. So you probably will not expect the average to be too different from the individual value. That's why it looks very similar. Okay, so as you can see, this is the plot of factor B times factor A. Okay, so here each the horizontal axis corresponding to the 3 level of B, and 4 different color and different symbols corresponding to 4 different levels of A. On the other hand, this graph here at the lower bottom is in the horizontal fact we have A, the 4 levels of factor A, and the 3 colored line corresponding to 3 different levels of B. Okay, so it's just different way to look at interaction. Now, if we focus on the one on top. Now, if you choose not to show all the plots, then by the other option is to show this one. Okay, so the interaction between A and B. Okay, now let's explain the factor B and A. We can see that the largest response time corresponding to when the memory size is the smallest, number of program open is largest, which is 4. That will give us the smallest, largest response time. On the other hand, if you look at this point here, corresponding to the level 3 of factor B, which is the largest memory size, and corresponding to level 1 of factor A, which is only have one computer program open. Okay, so in this case, the response time is the lowest. Okay, so this seems to be an interaction effect. Now, however, whether it's significant or not, you still need to go back to the ANOVA. Now, the ANOVA here tells us the interaction term, the p-value here is 0, close to 0, so it's significant. You can also go to window to take a look at. Now, if we look at in the main effect, we can see, first take a look at the factor A as the number of programs open becomes more increase, then the response time will also increase. On the other hand, if you look at factor B, as the memory size increase, the response time will decrease. Okay, so we can see there seems to be a significant main effect for both factor A and B. However, to see whether they are really significant or not, you still need to go back to the ANOVA and look at the p-value. So both of them are close to very small, so we can say that they are significant. Okay. So now let's take a look at the fractional factorial design. Okay. So again, the fractional factorial design is just a more efficient way to run experiment, especially useful when you are doing screening. You have a lot of different candidate factor. You want to know which might be significant, but you have so many different factors to consider. If you do a full factorial design, you have to run a lot of experiment which will require a lot of time and resources. So you might not want to do that at this stage. So for screening purpose, you might also want to do a fractional number of them so that you can filter out some of the non-significant factors. Okay, and focus on the significant ones, and then maybe do a full factorial design for that and see their interactions. Okay, so the way to do this is go to Stat, DOE, Factorial, create factorial design. Okay. Now, so the example that we are looking at have 6 number of factors. Okay, so we see that in the initial we want to screen those 6, right? And then you go to design. Well, actually, because in all of those 6 factors, we only have 2 levels, so there's no reason to use the general full factorial. So we can go to the 2-level factorial. Okay, so you go to design, and you can also display the available design. Okay, so here's all the available design. We can see when we have 6 vectors, if we look at this column corresponding to 6, now a full factorial design will require 64 runs, but instead we're only going to have a revolution 4 design, which is only run a fractional number of the 64, which is 16. Okay. Now if you go to design, go to 1/4 fraction, it says resolution 4, and then you hit OK, and you hit OK. So so what it will return is the experimental design. Okay, so basically it tells you that you have 16 runs. Okay, and here is the standardized order. Again, every time when I generate a design, it might be different. Now here is the for each of the experiment. So for example, for experiment 1, this is when factor A is at the high level, B is at high level, C is at high level, D is at low level, E is at high level, F is at low level. So low level corresponding to -1, high level corresponding to +1. And then here you can type in the response. Okay, so that's how we generate resolution 4 design. Okay, thank you. Okay, finally let's take a look at an example for MANOVA. Okay, multivariate analysis of variance. Let's say that you perform a study in order to determine the optimal conditions for extruding plastic film. So you measured 3 responses. Okay, so before we only talk about 1 response, but the MANOVA is extension of ANOVA. So basically you can simultaneously measure multiple response. So here we have 3 response. One is tear resistance, one is gloss, one is opacity. Okay, so you measured 5 times at each combinations of 2 factors. Okay, so the first factor is rate of extrusion, and the second factor is amount of additive. Okay, and each set at low and high level. So we have 2 levels for the 2 factors, and we have 5 replicate because you measure 5 times. Okay, so the data and examples are from Johnson, Witcher. Okay, I provided a reference, and also the page number is 266. Now let's use general MANOVA to test. No, okay. So first open the data file, then go to stat ANOVA general MANOVA. Okay. In the response, actually, let's first take a look at the data. Okay, so if you look at column 9 to column 11 corresponding to the 3 measures, okay, and then column 12 corresponding to extrusion, and the column 13 corresponding to additive. Okay, so we can see extrusion have 2 levels, okay, and additive also have 2 levels. And notice that for each combination of the factors, you have 5 replicate. So for example, the first 5 rows corresponding to extrusion at level 1 and additive at level 1, and then the next 5 rows corresponding to when extrusion is at level 1 and the additive is at level 2. Okay, so we verify the raw data. So you go to, then we can run MANOVA. Go to stat ANOVA general MANOVA. Okay, so the response, our response should be from tear to opacity. Okay, so you hit shift, and then you first click tear and then hold down shift key and then hit opacity and then choose select. So the response will be tear to opacity. Now the model, you will have the two factors. Okay. Now, because you also want to study the interactions, you will add this sign here. Okay. So the vertical line here. And then you go to results. Okay. Here, give you some options for displaying the results. So you can choose displaying the result, hypothesis, error, partial correlation, or you can choose not to. Okay. And let's say that you choose yes, and then hit OK. Now you can see the output from this MANOVA. You can see there's a lot of information. Those are not necessary for you to understand. Okay, it's way out of our scope. But you need to understand is we know the p-value, right? There's three tests for each of the factors, right? For extrusion, we can see all the three tests tells us that there's significant effect for extrusion. Okay, and then if you go down, you can see for the additive, the p-value from all three tests is about 0.025. Okay, again, it's significant if the level of significance is 0.5%. And then finally, you look at the interaction, extrusion times additive, and then all the three tests tell us that the p-value is 0.302. So it's not significant. Okay, so this is the end of the presentation. Thank you.